You've probably seen this classic magic trick. You run a plastic comb through your dry hair, hold it over tiny bits of paper, and watch the paper fly up to meet it. The comb essentially becomes a temporary magnet, effortlessly attracting those light objects right off the table. But look what happens if you try the exact same trick with a metal spoon. You can rub it through your hair all day long, but when you hover it over the paper, absolutely nothing happens. The paper stays perfectly still. Both objects are experiencing the exact same friction against your hair. If the act of rubbing is what generates static electricity, why does the plastic work while the metal fails? It seems like the electric charge on the spoon just vanished into thin air. The difference is found deep inside these objects, specifically the internal traffic rules that govern their atoms. Let's start with our first category, insulators. This group includes plastic, nylon, glass, and wood. Inside an insulator, the internal structure is incredibly strict. Outer electrons are rigidly locked in orbit. When you rub a plastic comb through hair, friction transfers extra electrons onto its surface. But because plastic is an insulator, these new electrons immediately freeze exactly where they landed. The material offers so much resistance that the charges cannot move. You end up with a high concentration of extra electrons trapped in one very specific spot. When that negative charge gets close to the paper, it actually pushes the electrons inside the paper bits further away. This leaves the top surface of the paper with a positive charge, which is why the two materials suddenly snap together. The plastic comb works because it acts like a locked parking lot. It holds the electric charge exactly where you rubbed it, giving it enough concentrated power to pull the paper upward. Now we look at the opposing category, conductors. This includes metals, like our spoon. Metals are packed with free electrons, zipping continuously through the internal grid. Carrying the same negative charge, they naturally push away from one another. When friction drops new electrons onto the surface, this natural repulsion takes over. The charges instantly rush outward, distributing evenly. Conductors are essentially open highways. They cannot hold a charge in one spot because the electrons are always free to run away from each other. This brings us to a crucial fact. Human bodies and the Earth are highly effective conductors. When you rubbed that metal spoon against your hair, it actually did pick up a charge, just like the comb did. But because the spoon is an open highway, the charge found an escape route immediately. It flowed down the metal, into your hand, and traveled through your body. Finally, the charge drained out through your feet, dissipating into the massive expanse of the Earth. If you wanted a metal rod to actually hold a static charge, you must hold it using a plastic or wooden handle to physically block that path. The spoon is essentially a victim of its own efficiency. It creates a charge just like the comb, but its atomic highway provides an immediate, unlocked exit into your hand. This invisible logic explains why certain materials behave so differently. Insulators lock charge in place, while conductors allow it to spread and flow. You feel this in action whenever you slide off a car seat in dry weather and get a sudden static shock when you touch the metal door handle. That sharp spark is the exact moment the charges trapped on your insulating clothes find a conductive highway to escape through your body. We see nature's version of this when massive amounts of charge build up in the sky. Lightning is trapped static electricity finding a sudden conductive path through the air to reach Earth. Whether it is a comb, a car door, or a thunderstorm, electricity is always just looking for the easiest way out.